Good afternoon. This is Mark Richardson with Vibrant Technology. I'm the marketing manager, and welcome you all to another Vibrant webinar, an MEscope webinar. Today we're doing a OMA curve fitting. This is our third installment of curve fitting. I believe we've had, well, let's see, the past 2 months now, we've had two other curve fitting webinars, and I think we still got some more to go. So we will stay tuned for that. But we got a good one for you today. I'm joined by my father, Mark Richardson Sr., the CEO and founder of Vibrant. And yeah, before we get going here, let me just remind everybody, we are on mute. If you have questions, we will get those questions answered at the tail end of the webinar. You could type those questions into the box there in the GoToWebinar panel on the right side of your screen. And we are recording this, so if you do miss anything, we'll get the recording put up on our YouTube page, probably beginning of next week, and you can go up there and review anything you may have missed during the webinar, or if you want to share it with others in your companies. Let's see, I think that's about it. Why don't we get going? We got a lot to get to today. Dad, you want to take it over?
Okay, thank you, Mark, and welcome to all of you. This is going to be packed with a lot of information today. Hopefully I'll get through it. I'm already excited about our next webinar. I'll kind of bring that up at the end. Brian Schwartz, who normally would be in attendance, he's one of our engineers. He generally handles all of the support questions, technical support questions for customers. Once you buy the software from us or license it. You can license it on a monthly basis. Go to our website, and we have customers that are doing that now. You know, especially consultants that are maybe not using it all the time, but when they get a customer where they can use MEscope for ODS work or modal work, that's a good way to go. Anyway, let's move on. As Mark said, we're going to do OMA, which stands for Operational Modal Analysis. And the term itself has been popularized by other companies that offer software in this business. There's some caveats with it, but if you have a running machine or a car on a test track or an aircraft or any kind of a mechanical structure where you can't measure the excitation forces, then you have to do the best you can with whatever data you can acquire. And certainly with any operating machine, a rotating machine in a plant or in a process plant or a power plant, that's the best you can do, is just collect operating data. So maybe some of you are in that business. Modal, well, we'll just get into it here, because here's kind of what I call the universal laws of modal analysis, and there's 4 of them. This is from 50 years of experience being in this business, not only providing software, but doing modal tests. Any structure with mass and elasticity will resonate, but forces must be applied to it in order to make it resonate. All modes are excited at all frequencies. Now, we'll see that in a minute when we get into curve fitting. Many people don't think about that very often. They think about, well, there's peaks in the data, so there must be a mode there being excited. Well, all of them are being excited. And how many modes do real-world structures have? Ideally, they have a uncountable number, infinite number, but then we usually deal with the lowest frequencies because they dominate the vibration response of the structure. And then we're going to look at an example today, actually both examples. All vibration is a summation of mode shapes. So we talk a lot about ODS. Our base package of MEscope is called Visual ODS. What is a ODS? What do we mean by this term? Well, it's an operating deflection shape. So it's a deflection of the mechanical structure at various points. So force motion at 2 or more DOFs, what we call DOFs. So in order to talk about a shape, we need to make more than one measurement. And then we can compare the motion at one point in direction relative to the motion at other points. It's a vector. An ODS has the components, each component has location and direction. So that's what we mean by a vector. Okay, here's a DOF definition. Each location and direction is called a degree of freedom, or a DOF. So these are terms that we commonly use. And then each vector component, or each DOF, also has magnitude and phase. And that's very important when we're looking especially at machine vibration. Magnitudes, of course, are important because that's going to dominate the vibration. The resonance might dominate it, but especially in machine maintenance areas, the phase from one point relative to another is very important. So how do we distinguish ODS analysis from modal analysis? Well, here's a definition. Modal analysis is a process of characterizing the dynamics of a mechanical structure in terms of its modes of vibration. So we're talking about dynamics here, not statics. When I put a static load on a structure, it causes deformation, a static deformation, but that's not a mode of vibration. Mode of vibration is a resonance, and it involves dynamics or motion. So what we call a mode is really the same as the term resonance, resonant vibration. We've all experienced it in the cars that we drive, or the washing machine shaking the house, or the house itself shaking here in California when an earthquake occurs. Those are all examples of resonances or modes of vibration. And there's three numbers, or three things. Actually, there's more than three numbers, but three things that define a mode of vibration. It's frequency, it's damping, and it's mode shape, which is again a spatial distribution of the resonance. And we call it a standing wave. Okay, we're going to talk about curve fitting. We're going to run some examples in MEscope. Here are the main steps that we use in MEscope for curve fitting. First of all, we need a 3D model because we're going to collect data on some sort of a test article. And again, as soon as we collect data from 2 or more degrees of freedom, points and directions, then we can talk about a shape, either an ODS or a mode shape. In MEscope, we support all different kinds of models. A stick model, which is just some points connected by lines. A surface model, which is points connected by surfaces, and we have various kinds of surfaces that you can have in MEscope to define the model. And then you can also import a photo model, and we use a third-party software package that will create a 3D model with points and lines and surfaces from photographs that you take of the test article. So we'll be looking at those also, and we commonly use those in MEscope. We need to get some vibration data into MEscope so we can post-process it, and there's a whole bunch of words here, but the important issue is that what we acquire or import is multi-channel ODS data. Now, what do I mean by that? Well, multi-channel means that we have connected it, collected it or acquired it with hardware that can simultaneously acquire more than one channel of data at a time. And then we create all kinds of functions from that. And again, here's some buzzwords, some approximations. TWF is a time waveform. So that's the basic data that we acquire, digitized time waveform from accelerometers or from a cell phone video. Now, we've done a bunch of webinars on that. We'll do some more in the future. That is our latest technology for acquiring time waveforms. A DFT, or a digital Fourier transform, is simply the FFT applied to time waveforms. IRF is an impulse response function. FRF is a frequency response function, cross spectra. Again, these are all plural because we need to collect more than one in order to look at an ODS and then curve fit that data to obtain mode shapes. And then there's something called an ODS-FRF, and I'll refer to this a bunch, especially in the second example. That's something we created here at Vibrant years ago. Well, let me move on. We'll come to more of a definition of it in the next slide. Animation in MEscope is probably its strongest feature. It allows us to visualize vibration either by animating time-based ODSs or frequency-based ODSs. So time-based, we sweep through the data, the TWFs, and frequency-based, we can put the cursor on resonance peaks or any frequency and use sinusoidal animation to modulate the shape, whether it be an ODS or a mode shape. Then we get into curve fitting and we extract modal parameters by curve fitting the ODS data. Finally, we display mode shapes with sinusoidal animation again. So, talked about a lot of things so far. Here's a little more definition of how we acquire ODS data. So keep in mind that all of modal analysis is based on curve fitting of ODS data, either sampled over time or sampled in the frequency domain. So we have very simple, in the bad old days of modal testing, we could extract mode shapes right from the time waveforms themselves if the test article was excited with a single frequency. So that there's still many people who do sign testing today so that they can focus on a single resonance at a time. Impulse response functions. I've done testing. We did some testing of space vehicles where we simply impacted the test article with an impact hammer and measured the impulse response at multiple points. Again, these are single channel measurements, but if we're going to look at ODSs or mode shapes, then we need to simultaneously acquire that kind of data. Then the DFT is simply the FFT of the time waveforms, and we can put the cursor on peaks in DFTs and look at the ODS, or we can curve fit that data also with what we call FRF curve fitting in MEscope and recover or extract the modal parameters. Auto spectra, again, this is used heavily in the machinery maintenance area. Simply measuring the peaks of or the peak values in the auto spectrum of what are called machine orders, or multiples of the running speed of the machine. The most common way of collecting data for modal and curve fitting in MEscope is what we call an FRF, and it's defined as the DFT of the response divided by the DFT of the force. Now, there can be many forces, so we need to acquire them all as time waveforms, and then process that data to come up with an FRF between each response and each force. That's called a multiple reference set of data. Transmissibilities, many people over the years have measured transmissibilities when they couldn't measure the force, so they just measured another what's called a reference response, and then did the arithmetic in their analyzer or in a computer, dividing the response DFT by the reference DFT. That can be problematic. You can't curve fit that data, but you can put the cursor, if you know where the resonant frequency is, you can put the cursor on that data. And again, it's ODS data, and animate an ODS from transmissibilities. However, well, let's go to cross spectra. That's the common way of calculating data, frequency domain data that can be curve fit, and we're going to look at that in a minute with an example. By using the DFTs, and there's a little bit of arithmetic there, the roving response, and again, we use a reference response and divide or multiply all the data by the conjugate, complex conjugate of a reference response. ODS-FRFs, why do we even consider this? The advantage of them is that the magnitude of an ODS-FRF is actually the auto power spectrum, or the auto spectrum of a roving response together with the phase of a cross spectrum between the roving and a reference response. So that gives us data that we can actually curve fit. We can window it and curve fit it just like the cross spectra. And but we can integrate and differentiate that data. So let's say we take some data off of a video, that's going to be in displacement units. And if we take data off of some accelerometers, that'll be in acceleration units. Well, we can integrate one and differentiate the other and compare answers. So it's a way of looking at data in velocity units, and many of the standards for machinery maintenance are written in velocity units. So let's move on though. I'll keep bringing that up because OMA certainly is used for rotating machines and plants and equipment of any kind, where the dominant forces, although we can't measure them, are multiples of the running speed of a motor in the test article. Okay, here's another way to look at curve fitting. It's a data reduction process. So we collect thousands of time waveforms, TWFs. We calculate maybe hundreds of FRFs, and we curve fit them, and we end up with a handful of modal parameters. But here's the difficulty with making FRF measurements. We're going to curve fit this data with what's called an analytical form of an FRF, or it's the inverse Fourier transform of an FRF, which is an IRF. One of our curve fitters, called a complex exponential, actually curve fits the time domain data. So we'll look at the different fitters in MEscope, and our approach is to use multiple fitters on your data, and that way, if they're all getting the same answer, and we talked about this in the previous webinars, that's the way we confirm that curve fitting is working well. But all forces and responses must be simultaneously acquired. So that is the difficulty with any operating machine. And in many cases, we can't, there's just no way to measure the forces. They're either internal or they're distributed. But we can measure cross spectra and ODS-FRFs. We talked about them, but they must be windowed. And we have a special window in MEscope called a deconvolution window. And we'll see the effects of that in a minute. So here is what we mean by FRF curve fitting using a stability diagram. The best fit of an analytical FRF function to a set of experimental ODS data. So let's just move on and do some curve fitting here. Dan, I'm in a webinar right now. Had to answer a phone call. One of our resellers, Dan Embray, who does a lot of these webinars, he didn't realize that I'm doing one today on modal. Anyway, interruption. Here's what we do in MEscope. This all happens behind the scenes. This is why you pay good money for MEscope. It does a lot of calculations to get you to the final answer of FRF based, or using an IRF, curve fitting the IRF functions to get to a set of modal parameters. This is a good picture of what happens with all curve fitting, and we'll see this in both examples. It's a summation of resonance curves. So back to one of our fundamental laws, the universal laws of modal analysis, all vibration is a summation of mode shapes. And these here, it's saying it a little differently. It's a summation of resonance curves, one due to each mode. In MEscope, we've got several curve fitting methods, a local SDOF, a local MDOF. SDOF stands for single degree of freedom or single mode. MDOF means multiple modes, multiple degrees of freedom, global, and multi-reference. And each of these has advantages and disadvantages. And it's kind of a food chain in a sense that the advantages that I have in local SDOF are, well, here's a disadvantage, closely coupled, because I can't curve fit one mode at a time. I go to multiple mode at a time, and I can identify the properties of local modes and node points are closely coupled, but it doesn't do well with local modes or nodal points where the mode shape doesn't exist. Global is our most popular. We call it a quick fit. It will handle local modes and nodal points very well, but it will not handle repeated routes. So then we need to go to a multiple reference. That means we need to collect more data so we can get a better look from different references at the ODS data. The curve fitter then can identify repeated routes. A repeated route is the two different modes with the same frequency, but different mode shapes. That's what we mean by a repeated route. However, we're going to use a curve fitter here in a minute, and it uses a stability diagram, which doesn't work very well with mass loading or frequency shifts. Here's something we call modal coupling. When data looks like this, each resonance peak is kind of isolated by itself. I can use an SDOF curve fitter. If my data looks like this, I have to use an MDOF curve fitter. So here's a little more detail on the 4 different types of fitters. I'm going to move along here pretty quickly. Why do we use a stability diagram? Well, it's because our mode indicator, which we need for the MDOF and the global fitters, what we call the polynomial fitter in MEscope, it needs to know how many modes are in the data in order to curve fit it. So a stability diagram gets rid of that restriction of counting resonance peaks in the mode indicator, because it just curve fits over and over and over again with more and more modes in the curve fitting equations, and then we clean up the picture into what we call stable poles. Something else we use to compare mode shapes, we covered this before, again, the MAC or modal assurance criterion measures the collinearity between 2 mode shapes. SDI, this is something unique to MEscope. This measures the difference between 2 mode shapes. So we're going to see both of these numerical calculations in use when we compare curve fitting answers, and this is a common way we do it in MEscope to compare mode shapes from one curve fitter versus another. All right, we're going to go into using application note 41, and the title is Extracting OMA Modes from Random Responses. So this is a simulation. We have other app notes where we actually take live data off of a bridge and some other test articles, but this app note actually uses what we call our MIMO calculation in MEscope to compute the response of MEscope, or of this Jim beam, using the mode shapes of the Jim beam as a dynamic model. And we're going to excite the Jim beam with 2 random forces, and this is our MIMO modeling here, and we're going to use a formula or a command called transform outputs. So we're going to feed in some random inputs to the Jim beam. We're going to use the mode shapes, the experimental mode shapes, what we call the EMA mode shapes, an EMA modal model of the Jim beam, and then we're going to compute random outputs. And then from those random outputs, we're going to compute cross spectra. And here's a picture of what some of them look like. Then we're going to go, okay, here's a picture of the curve fitting. And then we're going to compare the OMA mode shapes with the original EMA mode shapes that we used to simulate this random response due to the 2 random forces. So let's go ahead and do that. All right, so app note 41, the VT-max file, which is an MEscope, where we store all the data for MEscope. Now, one of the standard features in MEscope, and those of you who own it probably have never tried this, but it's what we call a scripting language. And we can write scripts, which is just a spreadsheet of MEscope commands, and each script has a hotkey, and when I press the hotkey, it will execute the script. So here are all the hotkeys for this project. So you can see I've got a reset key here, and that pops up a little button that says, or a little window that says, you know, press the hotkeys in order. So I created all these scripts and then saved them with this project. All right, let me push the first one. And this puts up a little dialogue, again, from the script telling me what I'm looking at here. Here's the 2 random forces. We can create those in MEscope for doing this kind of simulation work. And then here's the FFT of those 2. So these are the DFTs over here. You can see they're labeled as DFTs over here. These are labeled as TWFs. Time waveforms. So here's the time waveforms, here's the spectra. So these spectra were created with a bandwidth to cover 0 to 2 kilohertz. And when we take operating data on a machine or out in the real world, we don't know what the bandwidth of the excitation is. It could be random. It could be the wind blowing on the test article. Could be a machine running, gearboxes, all kinds of things. Let's move on. Here's the unit modal mass mode shapes. Now those are scaled to in a certain way so that we can synthesize FRFs. However, we're going to scale them over from UMM to what are called residues. So these, you can see, these are residue mode shapes, magnitude and phase. Over here are UMM mode shapes, and normally a mode shape has no units, but when we scale them to UMM, we save the units, and you can see they're in inches per pound second. Now let's go over here and look at these. This is more realistic in the sense that these have the units of G's, acceleration, divided by pounds of force multiplied by seconds. That's because these are the numerator terms. We went through some of the math in our previous webinars. Let's just go ahead and compute some random responses. So we're going to use the MIMO calculation. You can see it's synthesizing FRFs, and it's doing the multiply between the FRFs and the DFTs of these inputs. And now we've got over here, we computed DFTs, and then we inverse Fourier transform them back to the time domain. So here's our original time waveforms of the 2 random forces. Over here in G's are the time waveforms of 99 degrees of freedom. So where did that come from? Well, let's go back here real quick. There are 33 points on this Jim beam, and each of them has motion in the X, Y, and Z. So 33 times, there's where we get the 99 degrees of freedom. So let's go back to our examples here. So those are the random responses. Now we're going to compute the cross spectra between all those random responses and a reference. So if we look at the DOFs over here, we can see these are the random responses. Well, there's a special one down here at the bottom, which is what we call an envelope. I can click on that, and that's an envelope of all my FRFs, so I can locate peaks, and this is really handy for other reasons, especially when we take data from a cell phone video. But here they are, 99 of them for all the DOFs of the Jim beam. So this is what they look like. We can scroll through here. Well, let me just scroll through and look at some of these. So you can see some peaks in here, but it's still relatively noisy. Now, we did 25 spectrum averages from this data, because if I look at the amount of data I have over here, data block options, let's just go in here. That's the wrong one. I want the properties of the data block. There's 50,000 points. Each of these traces here, each of these TWFs has 50,000 points in it. Over here, each of these has 1,000 points in it. So we need 2,000 points to compute a DFT, the rule of the FFT. But let's just move on, and you can see how 50,000 points would give us 25 averages over here. Now we can average even more, but let's just go ahead and do some curve fitting here because we're kind of running out of time. Okay, so the curve fitter has run, and we can see that over here is the fit function on top of the data. The data has been windowed, so that cleaned it up a whole lot, but you can see there's still a little bit of noise in there. These are windowed cross spectra. Now, what we call them in MEscope is an OMA FRF. Let me just display the Bode plot, which is magnitude and phase. So now you can see the phase here. When we go through a resonance, normally the phase will go through a transition like this of minus 180 degrees. But with this type of data, it's not clear that it's ever going to do that. But the curve fitter can still curve fit this after it's been windowed. And you can see we got a pretty good fit, except for the envelope here at the end. But all these other ones, both magnitude and phase, that's what we call a complex function. And down below here is the stability diagram, and it's been cleaned up. If I go over here and look at, again, we looked at a lot of this last week. If I show all, that's going to show me all the answers that the curve fitter gave me. And then we run it through a filter, and you can see that some of the answers just keep coming out the same. If I filter the data with a frequency tolerance, a damping tolerance, and a minimum number of stable poles, a pole is frequency and damping, then I end up with a nice clean stability diagram like this. And then the average of each of these stable poles is saved over here, along with the numerator term, the residue magnitude and phase. So this is all of our curve fit data for all these resonances. So we found 10 modes, frequency and damping, and you can see as I scroll through here, the different measurements, the only thing that changes is the magnitude and phase of the residues. Those are the numerators. The frequency and damping are assumed by every curve fitter, and certainly in modal analysis, we assume the frequency and damping to be the same. Let's move on. So we've curve fit them. Now we're going to compare answers. So here is kind of the round trip. On the left are the OMA mode shapes being animated, and we're doing a sweep animation here through the shape tables. So we got the OMA mode shapes on the top, the original EMA mode shapes down here on the bottom. And so the EMA mode shape is being animated over here, the OMA over here. And here's the MAC calculation, which shows us that, in fact, they are collinear. Now, the values of the two shape tables may be quite different because we started off with UMM mode shapes here. So those values, you can see some of them here, magnitude and phase. Let me scroll this up so we can look. Quite different values. So if we were to display the SDI value for these different mode shapes, it would be 0 because their magnitudes are quite different. But the MAC value is very useful for just saying, yeah, this is the same mode shape, even though it's scaled differently from one set of data to the next. These are the same mode shapes because the MAC values are all very close to 1, 99%. MAC values always go between 0 and 1, so do the SDI values. MAC shows the collinearity, and SDI shows the actual difference in values. And again, these are complex valued, so complex arithmetic for vibration is what we use always. And then we can also just visually, we don't have these in a shape table. We could put them in a shape table and compare the numerical values. But the curve fitter, here's what the curve fitter gave us for frequency and damping when we curve fit the cross spectra. And down here is what we started with to synthesize the random responses due to two different shakers. Okay, I'm going to put this down and let's go to the next example. And that is down here. So this is app node 52, where we take some order-based ODS data and we curve fit it with some analytical mode shapes. So this is pretty interesting. And again, this is going to verify that doesn't matter where we get this ODS data from. In this case, we got it with some accelerometers. We could get it from a video or from prox probes or any other sensor, laser, if we use a laser vibrometer. But we're going to curve fit this ODS data, which is what we did in the previous example. Also, we curve fit ODS, what I call frequency-based ODS data over a frequency, the span of the cross spectra. Here, we're going to just take values at the peaks in a set of ODS-FRFs. And we call that we're just going to take the peak values of the first order ODS, or the running speed of the machine. So you can see a little picture here of this rotor kit, some accelerometers mounted on it. This is a laser that can measure the RPM. So we know exactly what the RPM is, although it's not needed because we can see it from the ODS, the peak in the ODS-FRF. So what we're going to do is run it at 3 different speeds, and then we've already saved the 3 ODSs into a shape table, and we're going to curve fit each of those with a set of mode shapes. All right, well, the ODS-FRF data was acquired at 8 points. You can see the points are numbered. This is it's really just the surface model. Well, I think it may be a photo model because we'll see, no, it's a surface model. It's just a surface model, but very realistic. The previous Jim Beam model was that was a surface model also. We didn't actually animate with the photographs on the model, but each of these models we can have photographs pasted onto onto the surfaces, but these are just surfaces here. This data can actually be taken not with an accelerometer on all 8 points and simultaneously acquired. That would require a 24-channel system. But if we use a reference, and that's how we compute ODS-FRFs and cross spectra, we can use a uniaxial accelerometer, and that can be anywhere on the test article. Doesn't matter, it's not important. What's important for the ODS is the DOFs of the roving accelerometer. In this case, a triaxial accelerometer that was attached to each point. So we can actually acquire data on this machine at any running speed by starting the machine with the accelerometer in one position, then moving it to the next position, acquire some data, next position. And that's generally how machine maintenance is done in the field with a 4-channel. We're going to do curve fitting with some FEA mode shapes. Now, MEscope has in it, one of the options is the ability for a simple model like this to calculate its FEA mode shapes. And so that's what we did in this, for this app note. But only of the base plate of the machine and the 2 bearing blocks. So what we're going to do is curve fit mode shapes of the base plate and bearing blocks to the ODS data of the running machine. And we're going to talk about something called modal participation and then shape expansion. Now, the interesting thing is that FEA modeling is another whole business. Mode shapes are a function of the boundary conditions, but the easiest way to model the modes of a structure or any mechanical structure is with free boundary conditions. So that's what we did here. But of course, the modes of this machine are not free. The real world modes have real world boundary conditions. So that means they're going to change. But what we're going to see here from curve fitting is that we can actually curve fit these free mode shapes to ODS data that reflects the boundary conditions, and we get a good curve fit. So only the mode shapes themselves are used. The frequency and damping aren't used in this type of curve fitting. This is just solving a set of linear equations. We talked about that in a previous webinar, that's really all curve fitting is, in its simplest form is fitting a straight line to your data. That's similar to what's going to go on here in this. We're going to measure what are called participation factors, and these are complex valued. We're going to fit some normal mode shapes, which are real valued, plus and minus, to some complex ODS data with a least squared error curve fitting method. We're fitting linear equations of the mode shapes to the ODS data. That's what's going on. Then once we have the participations, we can expand our experimental data using the participation of the FEA mode shapes in a synthesized ODS, if you will. And what this shows us is the universal law of modal analysis. All vibration is the summation of mode shapes. So let's just go take a look at that. Okay, I'm going to close this, or let's just open, well, we'll close this project first. And you can see it wants to save a bunch of stuff. I'm not going to save anything in this project, and I'll just go and open up project app note 52. And again, this project has scripts associated with it. So we're just going to press hotkeys in order and let the scripts do the work for us. So here's the first one. It says FEA mode shapes. So this has just executed a whole bunch of commands in MEscope to rearrange the windows and show us the mode shapes of the base plate and the bearing blocks. So the first 6 modes are what we call rigid body modes. This is just a body in space with no boundary conditions. And it's got 6 modes of vibration. They're called rigid body modes. 3 of them are rotation and 3 of them are translation. I can go back here. There's a translation mode and there's another one. And, you know, we kind of get them mixed up here. They all look like translation. Well, there's a good rotational mode. There's another good rotational mode. So they're just a body in space with 6 modes of vibration. Now this mode at 269 Hertz is a, you know, provided that I've built a good model with the right elastic properties and density of the aluminum material, there it is. And I've made a very stiff joint between the bearing blocks and the base plate, even though they are actually screwed on there, but we're just assume that it's a very stiff joint there. And you can see these are there's 4 flexible modes now. Very, you know, first bending, what we call first bending, and then first torsion. Because this is not axisymmetric, it's not a symmetric structure. You know, the torsional mode is a little different looking, but these are FEA modes. And there's another bending mode. I'm gonna call that second bending, and then a second bending involving the bearing blocks. So those are typical mode shapes. And as we said, with a fundamental law, all vibration, and again, the ODS that we measure from the real machine is a summation of these mode shapes. So that's what we're going to prove here by curve fitting those 10 mode shapes to the experimental ODS data. So here's a picture. And over here on this side, we're looking at the machine being animated and the rotors are going around and so forth. And we got some springs modeled underneath the machine. Those weren't modeled in the FEA. We just had the free mode shapes. And then the rest of the animation here is what we call geometric interpolation. And that's another feature in MEscope, where I've only got 8 measurement points and 3D motion at each of those points, but I've got a lot more points in this model. So they're all being animated with interpolation. And of course, the rotational part up here was interpolated from the motion of the bearing blocks, because it's that shaft and rotors are just sitting in the bearing blocks with some bearings. So that's a pretty realistic animation. Now you can see that, you know, we again had to make some choices about the geometric interpolation, but this is the real data at the cubes animating the model. Now over here on the right is what we call an expanded ODS, and we got that by curve fitting the 10 FEA modes to the operating data. And now we got a nice smooth animation over here, because those mode shapes define the motion at all the points on the base plate and bearing blocks. Up here is a measure of both MAC and SDI. So what it's saying is that these 2 mode shapes at the points where they're common, the 8 points and the 24 degrees of freedom, they're 80% alike. That means that the curve fitting did a pretty good job of matching those mode shapes up to the data. Over here is what we call the participation of the 10 FEA modes, shape 1 through 10, with the 24 degree of freedom ODS. So this is showing that modes 2 and 3 of the rigid body modes, as well as mode 1, combined together in a linear combination. So if we just take the first 6 modes here, they all participated in the ODS. Let me just rotate this around. But we also got some participation of the 7th mode and the 9th mode. So this is showing us that there was some deformation, because those are the flexible body modes. That's where, you know, number 7 was the first bending, and number 9 was a torsional mode, like a second torsion. So that's how everything participated in the 985. Now let's go to the 1440. So we speed the machine up a little bit, do the curve fitting all over again. MEscope's doing this with its script. Now you see a different participation. Mode 3, mode 5, mode 6 are dominating the ODS. And when we compare the expanded ODS here on the right with the original ODS over here, you can see that they're now 91% alike. So that's pretty good, both. And this is saying that the numerical values are the same, and they're collinear. Let's go to the next one. 2280, this is about as fast as this machine will run. So it says, you know, 24 DOF ODS on the left, and there's 1938 degrees of freedom in the expanded ODS on the right. So that's why we have you know, there's just a lot of data there that's animating that picture. Now, if we look at the real data, though, the reason now we're 95 or 94% alike, but you can see the real data. These accelerometers were just stuck on with magnets. You can see kind of a wild point here, but the curve fitting over here gave us a nice smooth motion for that point. Let's put some magnitudes and phases up here for the bearing blocks. Well, let me show you these real quick, and then we'll go back and look at magnitude and phase, because this curve fitting does a very good job of, well, I got it up here already. Let me go back, and we got two things going on here. I'm going to turn on magnitude and phase. So we do that here. Magnitude and phase, this is the deflection menu. These are all the point graphics that we can put on. So this is showing for the, where were we here? The 985 RPM ODS. Let me get this out of the way. Here's the values in inches per second of the original data at the bearing blocks. Those are realistic numbers. Here are the curve fit values over here of the mode shapes. Remember, those were normal modes. They weren't even complex, but the phases, because the participations, and we're just showing the magnitude over here of the participation, but there's actually a magnitude and a phase to each participation that was used to expand the original data using the mode shapes, and the values come out very close, you know, 0.2 in the X direction and 0.14 in the Z direction, the vertical. So you can see that with this ODS, there's just a lot of motion in the X direction. Now the X direction here is the, you see, don't look down here. The X direction is the local axis here that's back and forth. So that's where the primary motion of the machine is at that speed. Let's go look at the 1440 and see what it looks like. Okay, so here we are with the 1440, and we've got some, again, look at those phases. They match up almost perfectly. And the motion is over an inch per second on the inboard rotor, quite a bit more motion on the outboard rotor, again in the transverse direction. So this is very realistic, to the degree that the accelerometers were calibrated properly. We're getting some very realistic motion of this machine in inches per second. And then at the highest speed, you can see that we're getting a whole bunch more motion here of, again, the machine Now there's a little more divergence in between the curve fit result, but the phases, if you look at the phases, those are very close. Anyway, that's curve fitting, and let me just turn off this deflection or the magnitude in phase, and then we'll go back and take a look and see. This is, okay, we're getting that up again. Let me see why that's coming up. We got it. Okay, so we'll turn that off. Here's a comparison between the expanded ODS at 985 and the expanded at 1440. And you can see that they're drastically different. The values of MAC and SDI are very low. And one more, and then we're going to quit, Mark, and entertain some questions here. So here's how the ODS changes when, again, very poor correlation between those two ODSs. This is the 985 over here on the left and 2280 RPM on the right. Okay, let's wrap it up and answer any questions.
Okay, if you got any questions, go ahead and type those into the questions box there. First question we got here, it says, you showed that the mode shapes of OMA and EMA are very similar, high MAC value. In which cases, let's see, in which cases the results of OMA and EMA will be more different?
Well, in that one, it was a simulation.
Results, yeah, go ahead.
Yeah, we started out with some EA mode shape. So we were trying to, again, prove through the round trip of synthesizing. Let me go back, we can run through the whole thing very quickly here. I'll close this project and we'll just go press all the hotkeys again and talk about what we actually did. So EMA mode shapes, if I measure the forces, and that's how we got those mode shapes in the first case, we went through and actually got these mode shapes. These are experimental mode shapes, what we call, experimental or EMA, but they've been scaled in a certain way so that we can synthesize FRFs from them. Residue mode shapes are really what we need to synthesize the FRFs. Those are the numerators of the FRF for each of our measurements here. So when we go through this process of computing random responses, that's where we're using a command in MEscope, what we call one of our MIMO commands, where we're going to take the random force signals, these two random force signals, FFT them, and here's the spectrum of those, the DFT of those two forces. We're going to synthesize the FRFs and multiply the FRFs by the DFT, and that gives us the DFT of the responses, and then we inverse Fourier transform that. So we can go back here and real quickly look at that block diagram, because that's right here. This is several steps here. The first step was to do the transform outputs. Now I'm not going to go into the script that did all that, but the script executed this command and computed the outputs, and then from those, so it was a simulation of kind of an ideal random response, really. So when we go through this calculation here, this is going to synthesize the FRFs with and then inverse Fourier transform, so that we end up over here with these responses. And if we look at the data block properties, there's 50,000 samples in these responses. we start out with 50,000 samples over here, and we synthesized FRFs with 50,000 samples. We did the multiply in the frequency domain and then the inverse Fourier transform back here to the time domain. So we did all this right here with that one button press. FFT to the frequency domain, synthesize the FRFs, inverse FFs, or do the multiply, and then inverse FFT to get the responses. Then in the next hotkey, we're going to calculate these from the responses. And you can see they're kind of noisy. So cross spectra. So here are the noisy random responses. Now, I think what the question was implying is if I do a normal modal test, either with impact or shaker, and I calculate FRFs and curve fit them, am I going to get the same thing if I do an OMA where I can't measure the force? Well, what we're assuming here, and what actually we synthesized or we simulated here, was that the force had a broad spectrum. It was random, it was broad, and it covered the whole frequency range of 0 to 2 kilohertz. So we guaranteed that we excited all 10 of those modes that were from DC up to, I don't know, 1550. I guess this was the highest frequency right here. So when I go into the curve fitting, first of all, we windowed it. That's what cleaned it up. We had to use that window to make it look more like an FRF, but the curve fitting was very fast, and it curve fit these windowed cross spectra, which is the most common. Now we can curve fit the ODS-FRFs also, but they don't curve fit as well as the cross spectra. Again, both of them have to be windowed with what we call a deconvolution window. That kind of recovers the effects of the reference response from the data so that we get something that looks like an FRF of the roving response, even though we didn't measure any of the forces. So again, kind of reiterating the answer to the question, if we don't know anything about the forces, the best we can assume if we're going to pull modes out of the cross spectra like this is that all these peaks, these resonances did get excited somehow by some force. Now we know in a rotating machine, the peaks only show up at the multiples of the running speed, but they can show up at other frequencies also because of excitation, gearbox, gear mesh. Those are typically all multiples of the running speed, but those could be other peaks that are not necessarily multiples of, they're just resonances getting excited by random forces that we can't measure. So again, the best thing is to measure the forces, one or multiple. In the case of a hammer, we went through the first 2 curve fitting sessions where we just curve fit FRFs. This is where we can't measure the FRF. Anything else, Mark?
Not at this time. I do want to remind everybody, if you're interested in getting hands-on modal analysis training, our partner Jim Steedman at NavCon Engineering offers a fantastic 4-day hands-on modal testing and analysis seminar out in California. And the next dates they have coming up are August 14th through the 17th. And then they'll also be holding another one November 13th through 16th. And you can get all the information at navcon.com. There you go, right
I'm putting this up, yeah, there it is. So
yeah.
Here's all the training courses right off of our website.
Right down there at the bottom, 4-day hands-on, Fullerton, California.
Well, let me just give you a little introduction to our next webinar. We've done 2 different app notes where the other thing about modes is that they're linked to the mechanical properties of the structure, mass, stiffness, and damping. So we have an algorithm in MEscope, it's one of our options, called structural dynamics modification. And the way that works It's different than FEA. We take a set of mode shapes for a mechanical structure, and we model mass, stiffness, or damping changes to the structure. And SDM very quickly computes a new set of mode shapes for the structure, which reflect those physical changes, mass, stiffness, and damping. Well, with any mechanical system, what you'd like to know, and especially if it's machinery running in a plant or out in the wherever, out in the real world, if the resonances change, can we correlate that with a physical change? Well, that's exactly what SDM does. Now, you've probably all heard about artificial intelligence. I own a Tesla. It's an amazing car. It can take 8 video pictures as I drive the car and run those through neural networks in the computer of the car and draw up a stick model, actually a surface model of all the cars around me and the curbs and the stop signs and the red lights and everything by using neural networks to process that data. Well, the Achilles heel of using a neural network is training it, because it's a model of your brain. And just like a child has to go through years of learning, you have to train the neural network with a lot of data, but you have to label the data. In other words, when you feed data in to train the network, you have to tell it, okay, here's some data for a stiffness change, or in the case of a machine, here's some data for misalignment or unbalance or soft foot. These are typical problems in rotating machinery in a plant. But with SDM, we can label all that data and set up a loop, again, a scripting loop, and do millions of modifications to a mechanical structure using its modes of vibration to predict what happens when we make all these changes. And then they're all automatically labeled. Now, we've done 2 tests like this already without a neural network, and we call it FACS, or fault correlation tools. And what FACS uses is the SDI algorithm. And so if you save ODS data into a database, and we have a machine-based database, we haven't shown any of that to you, maybe I will in the next webinar, and you label the ODS as, well, this is a machine running at 1,000 RPM, 2,000 RPM, 3,000 RPM. And then you, just like we did in the second example, the second app note, 40 or 52, we can compare that data using FACS, and we get a bar chart that shows us how much the data that we just took on the machine correlates with ODS data that we've got saved in a database, which has been labeled. This is, and we did 2 different examples. We did stiffness or tension of the cap screws on the gym beam. So let me put that down, and we'll just go back and look at the gym beam here real quickly. So that's one, and I'm giving you a little preamble here as to what we might cover in the next right here. So here's a model of the real gym beam. I got one here in the office, and those 3 plates are attached by cap screws. So probably 10 years ago, we demonstrated the ability to detect how much torsion was on those cap screws, because and just using modal frequencies. So one impact of the gym beam, curve fitting for modal frequencies, compare those modal frequencies with labeled shape data in the database that had frequencies associated with different cap screw torques. So I might go through all that again. That's in one of our app notes. The other one that we did was, and again, we could do this with soft foot, with a, stiffness of a foundation. In the second example, we didn't actually use real springs. Those are just geometric. But we could actually model the stiffness of this machine it's sitting on the table here. The table's moving, the rubber mounts between the machine and the table are all vibrating when it runs. But, well, I got off on a tangent there. We could do that. I'm not going to promise that one, but we also have another app note where we put different unbalanced weights on this outer rotor. And then we measured the ODS and we labeled the ODS data with the unbalanced weight, how many of the unbalanced weights were screwed into the rotor. And again, using facts and comparing one ODS to the next, you can identify how much unbalance that rotor has in it. So those are two examples that we've already done in the past. We haven't trained a neural network yet with SDM, but that's in the future because that will allow us to identify many more kinds of mechanical faults on many more different types of machines from ODS data or from the modal data that we curve fit to the ODS data. Anyway, that's enough said. I'm done, Mark.
Okie doke. Yeah, that's going to do it for us.
Okay.
Appreciate everybody joining us, and stay tuned for the next one. We'll get an invitation out here soon, and hope everybody has a great weekend. We will talk to you soon. Thanks.
All right.
Goodbye.
So long.